Welcome to third session on dual spaces, part of linear algebra. So in the last two lectures we defined linear forms or linear functions on a given vector space. We looked at a lot of examples, and in the second session we defined what is meant by a dual space, the dual basis for a given basis of V. We found what is meant by a dual basis. Then we also proved if V is finite dimensional, then V star, the dual space, is also finite dimensional, right? Okay, now we want to talk about what do I mean by concretely identifying a dual space. It may not be possible all the time, but we want to talk about it. In most of the important cases, it's a very easy description. That's what we want to look at. So let us get started. Yeah, as usual, this is my channel. This is my email ID. If at all you want to write to me concerning anything about the videos or the channel, please use this email ID. Okay. And you can download the list of videos on my channel from this place, 4dspace.mtds.org.in/EA for expository articles. You search for list of videos. This list contains descriptions, links of the videos, and the videos are arranged in order of learning. These will also be periodically updated. One of the viewers has agreed to do that for me. Thank you. Okay, and the updates will be announced through posts in my channel. Coming to this, the reference is a forthcoming article of mine which will be available on request. The request may be sent to this email ID. If you send to any other email ID, it will not be considered. Okay, so let us make sure that I shared the view thing. Yeah, so what we want to do is you want to talk about, okay, suppose V is a vector space, okay, and okay, V star it's a dual. See, it's a very natural thing for mathematician. Whenever you have some object, mathematical object, that is an object with some mathematical structure, like V is a vector space, you construct something new object. For example, here it's V, we construct a new object. Okay, this is set of all functions from X to R, but with some property, namely it should be all linear maps from V to R. Okay, it is L of VR, which is a subset of this. Yeah. Okay, right. So the idea is to understand, that is, find some other well-known object, okay, and say your new object is isomorphic to some old object W. In our case, what we need is I have a V star. This is a set of all functions from V to R, linear functions. What I want to do is, can I find a space W so that V star is isomorphic to W? This is a linear isomorphism. Okay, then I will think of V star as only as W. Okay, right. It's something like 1 by 2. I want to think of only in terms of decimal numbers. I will think of it as 0.5. So if I want to think of 1.20, I will think of it as 0.05. Okay, in decimal expansion. So if you are comfortable with decimal, I will think of it. Or if I want only this kind of rational numbers fractions, then I will think of this. Okay, this just get used to this kind of idea. Do not try to understand 100% of all these things. You should understand the principle with which we want to work with. Okay, so let us look at the simplest case. Simplest cases, let us start with Rn. Okay, now so far I never said anything. Now I think of this as column vectors, that is set of all x, so that x is of the form x1, x2, xn, and where x, j are in R. Okay, that is, this is vectors vector space of column vectors. Of size n cross 1. Okay, n rows and 1 column. Think of them as matrices. Right. So, and what are the standard bases for this? EK will be 0, 1, 0, and this one is the kth coordinate. Otherwise, all others are 0. Right. Therefore, any x, I can write the summation xk ek. Whatever we wrote earlier is still correct. Right. Except I did not say how I wrote x. And I simply said EKs are natural standard basis of Rn. Okay, right. Now let us understand. Suppose F is a linear map from Rnc to R. Let us assume this is a linear. Right. Then since it's a linear map, I have natural basis singleton 1 here. Natural basis here Ek 1 less than equal to k less than equal to n. Right. So I can write down the matrix of A. Matrix of F. Okay, with respect to this basis, that's going to be, right? Notice that that's going to be f of E1, f of. See, do I remember? How do I write down the matrix? Let us recall. If F is a linear map from B to W, and if V1 to Vm is a basis, W1 to Wn is a basis, the matrix of F with respect to these bases, call it A, okay, and this is the first column, second column, and column. This will be a matrix of size. This is m dimension, this is n dimension, this will be a matrix of size n cross m, therefore there will be m rows. And what is C1? Let us look at f of V1, that will be summation sum. I will write it aj1 wj j equal to 1 to n. This will be my a11, a21, an1. Okay, this is f of v1 as a column vector. This is f of vm as a column vector. That's how we write. Now, therefore, f of v1, the matrices of A must be of type 1 cross n. What is that 1 cross n? The first column is f of u1. F of u1 is a number, therefore it's f of u1. Okay, and the second column is f of u2. That's a number, therefore f of u2, and this is f of en. Right? If you want to call it as a1, a2, an. This is okay. Thus, I can think of this as an element of Rn row, where Rn row is n dimensional, okay, row vector space. Right? Therefore, any f from Rn column vectors to R is identified with the row vector f of e1, f of en. That is right. Therefore, I have a map Rnc star to Rnr. This is a set of row vectors. Let us consider the map F. This phi of F is f of e1, f of en. Okay. Now, what do I know is this linear map is a linear isomorphism. This map phi is a linear isomorphism. Why? That is very easy. What is phi of f plus g? Phi of f plus g is f plus g of e1, f plus g of en. That is f of e1 plus g of e1 dot 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 f of en plus g of en. That is f of e1, f of en plus g of e1, g of en. Right? This is phi of f plus phi of g, and so on. Okay, and similarly phi, okay, respects scalar multiplication. And this map is 1 1 and on. Okay, these are all very easy. Why it's 1 1? Since this is already linear, it's enough to show kernel of pi is 0. Pi is linear. To show it's 1 1, kernel of pi is 0. That means what? F of E1, okay, pi of f equal to f of E1, f of En. This is equal to 0 0 0. This implies f maps. F is 0 on the basis. Therefore f of x will be summation x k, f of k will be 0. Therefore f is 0 map on. Okay, 1 1. On2 is clear. Pi is on2. Why? If you give me a1 a2 an, okay, we define f of x equal to a1 x1 plus an xn, which is same as saying f of ek will be ak. We know this is linear, right? Hence we have identified the dual of the column vectors with row vectors. So pause, review and proceed. Do you appreciate this? What we have done? We started with n-dimensional column vector, then its dual is order, okay, order n-dimensional row vectors. Okay, this is what we mean by identification. We had explained that. Okay, get used to that. Yeah, if you are a beginner, it will take some time. What do I mean by identification, etc. Okay, it's like saying that, you know, $1 equal to 85 rupees or 82 rupees, let us say. Then I identify 82 rupees as $1. It's just identification. So if I have to deal with dollars, I will simply say, if somebody asks me for $2, I will say 164 rupees I have to give. If I have dollar, if somebody asks for rupees, that means I have to give him. If we say someone have 164 rupees, then I have to give him $2. Okay, it's a kind of identification. Think of it that way. Okay, right. Let's go back. So let's look at another example. This is example 2. Suppose V is a pan-dimensional real inner product space. Then what we know is there is what we call reverse representation theorem. We had already seen that. What does it say? If f from B to R is linear, then there is a unique vector V in V, so that for all x in V, f of x is x inner product with V. Okay. Now we claim the map. Therefore, let us look at f star and let us look at this map. Let me call it as B suffix f for the time being. Okay. So for each f, let me associate to Vf. This is my map pi. Right? I claim this pi is a linear isomorphism. It is very easy to check, but I'll go through that again. Okay. What is pi of f plus g? Okay. So for f, I have f of x equal to x inner product Vf and f of g of x equal to x plus inner product Vg. Okay. These Vf and Vg are unique. Therefore, pi of f plus g, I have to say whether it is equal to pi f plus pi g. Right? Now, for f plus g, I will have some w. V of f plus g. So what we claim is V of f plus g is same as V of f plus V of g. Do you understand this? We will come to this later. Let us look at this. Okay. This is clear. Why? Because let us look at f plus g at x if fx plus gx, this is by definition, right? But this fx is x inner product vf and plus the x prime inner product vg. Is that okay? And using the bilinearity, this is x into vf plus vg, and this is true for all x and v, right? But I know this is nothing other than x v f plus g by our construction. Where does f plus g go correspond to? F plus g corresponds to f plus g. Where will it go to? It will go to v of f plus g, right? So, but there is a uniqueness part implies v of f plus g is v f plus vg, right? Now what does it mean? What is phi of f plus g? Phi of f plus g is v of f plus g, but v of f plus g is v f plus vg, but that is same as phi of f plus phi of g. Therefore phi is additive. Pause, review, proceed. Okay, and similarly, next what do you think I should claim? So let alpha be a scalar, then alpha f, then v of alpha f is same as alpha times v of f. We want to check. That is again easy, because alpha x acting on x by definition is x v of alpha f, right? Okay, but what is alpha f x by definition? This is alpha times fx, that is alpha times inner product x with v. This is by definition of scalar multiplication, right? Do you follow? But this is alpha times what is this? The vf, sorry, vf, right? But this I can write as x alpha vf. This alpha can go inside. Yeah. Now let us look at alpha fx. These are equal. Therefore, these two sides are equal. This implies by uniqueness implies v of alpha f is alpha times vf. Pause, review, proceed. Hence, the map phi from v star to v, f going to vf is linear. And since it's a linear, I want to say phi is 1 1 if and only kernel of phi is 0. If kernel of phi is 0, what does it mean? Okay, let f belong to kernel of phi. That means what? Phi of f is 0. That is vf is 0. That means what? F of x equal to inner product x vf, that is x0, that is 0. This is true for all x and b, therefore f is 0, right? So if f belong to kernel of f, then f is 0, therefore phi is 1 1. And phi is on 2 for the same reason. Given any given v and v, define f of x to be x inner product v. This is linear. And what is vf? Okay, so this is a linear, therefore there exists, I know there exists x, so that there exists v, so that therefore there exists vf in v. This is linear, right? By the Reyes representation theorem, there exists vf, so that this must be this. But these two are equal, right? This implies v equal to vf. That is, given any v, there exists a vf. Okay, so that okay, phi of f is given v, right? Therefore phi is on 2. So what does it mean? Therefore phi, the map v star to v given by phi of f equal to vf is a linear isomorphism. Hence, if V is finite dimensional in a part space, we can identify V star with V. Notice that in example 2, there are two crucial assumptions we made. First is V is a real vector space. Second is it's an inner product space. Finite dimensional inner product space. If you want to say, then there are three assumptions. Okay, V is finite dimensional and it's a real vector space. Third, it is an inner product space. Using that only we proved all those things. Okay, because real representation theorem is true only for finite dimensional inner product space. But for complex inner product space also it is true, but then we cannot identify V star with V because of simple reason. I will explain that in a minute. Okay, if V is complex, again finite dimensional, then again the result is true. There exists vector V, so that this is true. Okay, if F is a linear map, complex linear map, there is a unique vector Vf in V, so that for all x in V, Fx is inner product xBf. This is a true statement. So Real representative theorem is still true. But the problem is, I want to know what is alpha f. Okay, so alpha f acting on x, okay, this will be, for me, this will be alpha times fx, but that is alpha times x inner product vf. If I try to bring alpha inside, then you can see it is going to be alpha bar vf. And suppose this is true, x inner product v of alpha f, the uniqueness will tell me v of alpha f must be alpha bar of vf, not v of alpha f alpha. This is not true. Okay, so the map which you have from V star to V, namely V going to V of f, sorry, f going to V of f, is conjugate linear. What does it mean? That means, call this phi of f plus g will be phi of f plus phi of g for all f and g in V star, but phi of alpha f is alpha bar of phi of f, not alpha. Okay, so pause, proceed. Hi, I have to pause since the room was getting cleaned. Okay, let us go back and start again. Okay, now let's look at a third example. Hi, the room was getting cleaned, that's why I have to pause the video. We will start again. Okay, let us look at the third example. Now the third example is, let us look at m cross n/r. Right? Do you recall this was example 3? We had already done examples. Okay, yeah. You remember Aj, the matrices 1 less than or equal to I less than or equal to m, 1 less than or equal to j less than or equal to n. These are the matrices. Any matrix A is written as summation Aij, Eij, j running from 1 to n, I running from 1 to n. Right? And we found the dual basis f of Aij, we call it as Bji. Right? So we found out, what did we find out? Therefore f of A we found out to be double summation I and j aij and f of eij, that is equal to ij aij and bji, right? When you say this something like that, aij bji summation over j, right, and I, you know what this is. This stands for, yeah. If I have two matrices A and B, call it the matrix product C. What is Cij? Cij is Aik and Bkj summation over K, right? Therefore this is nothing other than, okay, consider the matrix B as this Bji, and what is the matrix of this size down? J runs from 1 to n and I runs from 1 to m. Therefore this is a matrix of type n cross m, right? Therefore I can take the product. This is m cross n matrix, this is n cross n matrix, though I will get n cross m matrix, therefore I will get m cross m matrix, right? And this is the ijth entry. Okay, this summation, this will be ith entry of AB, right? But that is what is the, if I have a matrix A, okay, suppose I have a matrix C which is a square matrix m cross m, C11 CMM, the summation C11 trace of C by definition is C11 plus C22 plus CMM. Therefore this is nothing other than, therefore what I found is f of A is trace of A B transpose AB, right? You understand this? Yeah. Okay. So I could also done the other way around. Let us look at. I could also return f of A as summation I and j. Okay, summation over I and summation over j b. Okay, ji aij. Okay. Therefore, the summation I can rewrite as summation over j and summation over I of bji aij. Okay. Therefore, this is again matrix B A I ith entry, but this will be of what size? This B will be n cross m, A will be m cross n. Therefore, this will be n cross n matrix. I could also return that way. Therefore, this is trace of BA. Is it okay? Right. So, what do you think I have done? So, if f from m cross n to R is a linear, there exists a matrix B. Where does it live? It's on n cross m R, so that f of A is trace of BA, where for all A in m cross n. Okay, I am writing a shorthand notation for this. Is it okay? So, and you can check as usual. Let us look at phi is a map for is m cross n R star to m of n cross m R, and for any linear functional f from m cross n R to R, I associate the matrix B. What is this matrix? This matrix B whose ij ji, okay, his entry is nothing f of ej. Okay, then I claim that pi is a linear isomorphism. Okay, I leave it you to verify. It is exactly similar to whatever you have done. Okay, first check it's a linear map and use it to show the kernel is 0, etc., etc. Okay, Please verify. Do not, okay? Before you proceed further. Don't take it for granted. This is the way you can master the subject. Okay? This shows that therefore the dual of M cross N or star I can identify with M cross N cross M R. Do you understand this? What is this one? This is M cross N, whereas this is M cross M. How? What is the map? Any F here goes to matrix B, whose ijth coordinate is F of E Ej. This is the ijth coordinate. Okay. Eij, this is the jith coordinate. Therefore, this is a matrix of size M cross M. Okay. So pause, review, proceed. Now do you understand? This example is very telling. I am looking at all linear maps from M cross N matrices to R, and I can say that it is isomorphic to all matrices of the type N cross M. Isn't it beautiful? Mass is fun, right? If you want to understand, it's just a plain theory alone will not make us get interested. This kind of good examples will be useful, and you will see in applications, in real life applications, you don't really deal with abstract vector space. You have to deal with matrices. Okay, so in such cases, this allows you to identify how to work with dual space, etc. Please learn these things well, because the typical abstract algebra course, these are not emphasized. Yeah, please learn that. Let me ask you a question. Why did I expect ever such a formula for a linear functional F from M cross N R to R? Namely, F of A is some trace of BA. The reason for this is something very interesting. That is, this is actually Ray's representation theorem. Is the answer. See, these are the things which typical linear algebra books will not say about these things. Okay? If you learn mathematics very in depth, then you will think about various connections, you will understand. So therefore, your conceptual understanding of mathematics will be much deeper and exciting. What is this? That is for M cross N R. Okay, I can introduce inner product. Okay, that is give me A and B here, then the AB goes to trace of B transpose A. Let me write B star. This is the transpose. I am looking at only real, otherwise I have to write complex conjugate transpose. Right? Now this is an inner product. I am not going to verify this. Okay, if you had learned my inner product space lectures, you have to watch, these things are all explained there. Okay, and this is a finite dimensional real inner product, right? Therefore, by Ray's representation theorem, there exists, let me call it an S in M cross N or such that F of, okay, if you are sorry, right? Therefore, if F is a linear map from M cross N R to R by Ray's representation theorem, there exists an S in where M cross N R such that F of A for all A in M cross N R, F of A is inner product of A with B. Now, what is this? This is a trace of A with S. Inner product of S transpose A. Therefore, I know my B is nothing other than S transpose. Therefore, are you following? It must, there exists an S with this property and there is a unique S, right? But I already found out this is nothing other than trace of BA. Therefore, by uniqueness, it will follow that my B must be S transpose. That is, or my S must be B transpose. Okay. Pause, review, proceed. And at this level, I expect you are a master's degree student, because bachelor's BSc students may find these things difficult. But if you had really followed, watch my lectures on inner product spaces, then this should be easy for you. Okay, right. Now let's go to the next topic, what is called annihilators. So it's annihilator. That annihilator means killers. Okay, what does that mean? Suppose V is a vector space, W is a vector subspace. I am going to, usually sometimes people write it WO, I write it W perp. Okay, this is a standard algebraic notation, and this is a notation on inner product spaces. I will use that notation. Okay, this is O for 0. This set of all F in V star, so that F is 0 on W. That is set of all F in V star, so that F of W is 0 for every W in W. Then this W perp is called an annihilator. The annihilator of W. So one can actually define for any subset S of V just a subset. Okay, but I am just sticking to only vector subspaces. Okay, this is actually a vector subspace. What? V star, because these are all subsets of V. Okay, that is very easy, because if F and G are in W perp, then F plus G at W and W is in W. This is F of W plus G of W, that is 0 plus 0, which is 0. And similarly, alpha F of W will be alpha into F of W, that is alpha into 0, which is 0. Right? Therefore, this is the vector subspace of this. Okay? Pause, review, proceed. So let us look at an example. Right? Okay, suppose B is a pan-dimensional real inner product space. Right? Then suppose W is a vector subspace of B. Right? But I know V star is V. That is any F going to the unique VF. Right? Therefore, what does that mean? What is W perp? W perp is set of all F in V star, so that inner product of, F of W is 0 for every W in W. Right? But this is nothing other than VF in V, so that what is FW? That is WVF is 0 for all W in W. But this is the orthogonal complement of W in B. This is set of all vectors VF which are perpendicular to W. You understand that? So this is the standard orthogonal complement of W in V with respect to the inner product. Pause, review, proceed. Okay, now let's look at another example. Suppose I have an Rn right? My vector space W is set of all x in Rn. This is, let us think of it as column vector, so that the coordinates x1 plus x2 plus xn is 0. Okay, where x equal to summation xk ek, then this is 0. Then we know this is a vector subspace. So what is W perp? It is set of all Fn. We know that is R and W, R and R, right? So that f of W is 0 for all W in capital W. This is our definition, right? But we know this is set of vectors, let us call y equal to y1, y2, yn in R and R, so that, okay, what is the f of y? That is y1 w1 plus yn wn is 0, because when I consider this as f, then what is its action? Do you remember that? Yeah, please go back. Okay, understand this well. Don't. Okay, f of w translates as y1 y2 yn equal to 0, right? Is that clear? So these are the y which are perpendicular to this. Okay, now what do you think it should be? Can you identify this? I want to say from this I want to conclude. Now remember, take w equal to, okay, something like ei minus ej 1 less than or equal to I less than j less than or equal to m. This belong to W perp? Yeah? Sorry, it belong to W? Because this is going to be 0, 0, 1 at ith place, minus 1 at ith place, and the sum is 0. Right? Therefore, my y1, okay, therefore y w is 0, right? This means this translates into, okay, yi minus yj is 0 for I not equal to j. That means all my yi's are equal. Therefore my y1 y2 yn is some constant, okay, c times 1 1 1. That is my W perp is R times E1 plus E2 plus En. Pause, review, proceed. Okay, so let us prove a lemma and then stop the lecture. Suppose W is a vector subspace of V, okay, then we want to claim dimension of V is the dimension of W plus dimension of W perp. Notice that if V is inner product space, if W perp stands for ortho complement, then we know V is direct sum of W direct sum W perp, which is orthogonal direct sum. Therefore, dimension of V is dimension of V, dimension of W plus dimension of W perp. Right? So this is, now notice that W perp is not living in V, it lives in V star. Okay, that is the only caution. But the dimension parma is still true. Okay, we don't get this because this W is in V, this is in V star, therefore I cannot talk about direct sum unless it's an external direct sum. In that case, I cannot say equal to V. You understand this? But what I know is the dimensions add up. How do I do that? Prove. Let us choose W1 to Wm, basis of W, and extend it to, okay, W1 to Wm, okay, V1 to Vk, a basis of V. extend this to a basis of B, right? Now let F1 to Fm, G1 to Gk be the dual basis. If you want, you can write W1 to Wm plus 1, Wm plus 1 to Wn, then this will be F1 to Fn, Fm plus 1 to Fm plus k. You understand this? I am just writing separately. Now what I want to claim is, notice that W1 to Wm and F1 to Fm, okay? If W1 to Wm is a basis of W, and then Fm to Fm is a dual basis. Okay, this is clear. Okay, therefore what I expect is this must be a basis for W perp. Okay, this is my expectation. Try to understand. You do not understand 100%, but try to understand. So what I want to claim? I want to claim if F belongs to W perp, then W is something like B1 G1 plus BK GK. That is, it lies in the span of G1 to GK. Okay, how do I prove that? Now F1 to Fm, G1 to GK, this is a basis for B star, and F belongs to B star. Therefore F will be some A1 F1 plus AM Fm plus B1 G1 plus BK GK. Right? This is unique. Now start with any Wi where I is 1 less than or equal to 1 less than or equal to I less than or equal to M. Then what do I know? Since Wi belongs to W, f of Wi must be 0. But what is f of Wi? It is A1 f1 of Wi plus A2 f2 of Wi plus Ai fi of Wi plus Am fm of Wi plus B1 G1 of Wi plus BK GK of Wi. Right? Now notice that F1 F2 Fm, okay, this is a dual basis, right? Therefore what do I know about G1 acting on Wi? That will be 0. If you want to think of it, Wm plus 1, right? This will be Fm plus 1 onwards. Okay, if I take any F from here, then its action on W1 Wm must be 0 because it's a dual basis. You understand that? Therefore these are all 0, and similarly this is 0, this is 0, this is 0. Therefore what do I get? I get A is 0, but this is 1. Therefore F is actually B1 G1 plus BK GK. Right? So in this what I have shown is this is 0, this is 0, therefore it must be this. Right? Now what? So F belongs to span of G1 to GK, but this is already linearly independent. You understand that? Therefore this set is linearly independent because this is a subset of F1 to Fm, G1 to GK. Therefore this is linearly independent, and this is linearly independent, and it spans W perp. Therefore this is a G1 to GK is a basis of W perp. Okay, therefore what does it mean? Now M plus K is N, but M is dimension of W, and K I can think of as a dimension of W perp equal to N. Therefore I proved the result. Yeah, that's what we wanted to prove. Notice that we wanted to prove this. We proved this is dimension M. We proved, okay, G1 to GK is a basis for W perp, that means dimension of this must be K. This K, sorry. So, okay, therefore we proved the result. And this shows M plus K is dimension of V. Are you following? So, what I have shown, if V is a finite dimensional vector space, if W is a vector subspace, then dimension of V is dimension of W plus dimension of W perp. Okay, this is reminiscent or analogous to orthogonal decomposition result in finite dimensional inner product spaces. So we will stop the lecture today. Okay, there is something we have to talk about, double dual, etc. And do you remember in finite dimensional inner product space, if you take W perp and take its perp, it will be W itself, right? So something similar we want to prove. We will do it in the next session. Okay, take care, stay safe, we'll meet again.